recording. And is it recording? Yeah. And share screen. Share screen. And let's all be happy. Can you see my screen? Yeah. So I can organize my stuff a little bit better here. Okay. So a quick recap. So we're talking about the Schwarzschild solution, right? Let's write it again. PS squared is just minus 1 minus 2 GM over R dt squared plus 1 minus 2 GM over R minus 1 dr squared plus R squared d omega squared. D omega squared is just d theta squared plus sine squared theta d phi squared. Right? And then we discuss the singularities, and then we discuss the motion of particles. Then we discuss particle trajectories. And we saw that we can write down a trajectory of a particle, reduce it to a 1D motion, which is 1/2 dr over d lambda squared plus v of r is half e squared. So it's very similar to what you did in your first year, and where v of r is the effective potential is 1/2 epsilon minus epsilon gm over r plus L squared over 2R squared minus GM L squared over R cubed, where epsilon is 1 for massive, 0 for massless. And we saw that, in fact, we end up with a result which is nearly identical to the form to the one that they derived by Kepler, like, I don't know, 500 years ago, 400 years ago, except for this last term, except for this term, which is the difference between the GR and the Keplerian. And then we discussed the various trajectories. We saw that there is a big difference. We introduced the ISCO, right, or ISCO 6GM, C squared, of course, to normalize. For massive particles, we saw that for massless particles as well, the trajectories can be curved. Well, you know, photons move along geodesics, so obviously they move on straight lines. It's simply that the space-time itself is curved. And then we discussed the classical tests of GR. I told you that there are 4 classical tests. There are several others, but these are considered to be the most classical ones, which is the gravitational redshift, something which we measured when we look at the spectral lines from you know, distant objects, which we happen to know the composition, or we think we know the composition, right? Stars. And then we talk about deflection of light. Right, so as opposed to Newtonian mechanics, where light being massless does not participate at all in the gravitational, is not affected by the gravitational potential. In GR, light is affected because the space-time itself is curved. And the same can be said about massive particles, which leads to a modification of the trajectories with respect to what you'd expect from a Newtonian formalism. And specifically, that leads to the precession of the perihelia of the inner planets. I should say deflection of light by the sun, if I'm to talk about the classical case. Today, we also have this deflection of light by other objects, which we can observe via space telescopes. And that's called gravitational lensing. And the third we said is the precession of the perihelia. of the inner planets. Right, so again, just as a reminder, right, the planets orbit the sun in ellipses, and perihelion is the point in the ellipse which is closest to the sun. And with every rotation, it is in slightly different locations. That's called a precession. And then the last one is called the Shapiro time delay. It's really a gravitational time delay of a radar signal, which is sent and being reflected in the vicinity of the gravitational field. That's called the Shapiro time delay. After Irving Shapiro, so the guy proposed that, and I don't know if he conducted the experiment himself or somebody else conducted it. He was definitely involved in that, which is a gravitational time delay. Of a radar signal. Sent and reflected. Inside the gravitational field. So we went briefly over describing those basic things, at least the first two. I did not give you the full derivation. I did give you the final results, and I explained to you the logic, how to produce it, but I did not do the full derivation. You can find it in the textbooks that I recommended that you read during this course. The reason why I didn't do it is because it's very technical and very mathematical. And, you know, conceptually is less just be 2 hours of deriving an equation, which will conceptually not give us more than what we have. Of course, it's very important to derive this equation because this is something which you can actually measure. And I stress again and again, you know, we're all students, we're studying physics. We're all studying physics, and you know, physics is not math. The theory, you know, can be beautiful and appealing and whatever you like it, right? But if it's not consistent with the observations, and at the end of the day, it will be thrown away as irrelevant. And so the reason why GR, of course, is accepted is because it had passed all the experimental tests that were carried since its formation more than 100 years ago. Of course, the last one is the detection of gravitational waves, which is also part of this theory, and something that simply does not exist in the framework of classical mechanics. It only lives here in the realm of curved spaces. All right, any questions about anything we said so far? No, that means that everything is clear. Look at your faces, and I'm not sure if everything's clear or not. I assume it's clear, but you'll get the new homework today. So just to make sure that everything is clear. Again, if you run into any troubles, then of course let me know. Some of you do, not all of you. I know some of you occasionally ask me for an extension, and I think I always give you one, but you know, pay attention because I keep on giving you homework. So don't get too much behind. Right? Basically, having just checked out, I think we have 3 more weeks to go before the end of the semester. I'm not sure when is your exam, but definitely this is pretty much a very good timing to review the material, and if there is something which is not clear to you, to clarify it, either personally with textbooks, either with your friends, either ask me. You know, do not wait until the last minute. I mean, you pretty much realize by now that if you wait until a few days before the exam, it's not a very good idea. All right, so as promised you, let's switch the color because now we're going to speak about black holes. So I'm sure you've heard about them. You know, it's very popular in the popular literature, popular science, TV shows, science fiction, whatever. Now let's do it in an ordered way, so we see what it's all about. So of course, the starting point we have is this Schwarzschild metric. This Schwarzschild metric, which is written here. Copy it again. So this is the Schwarzschild metric. Now, so far we discussed trajectories, but we always kept the condition that the radius of that trajectory is always greater than this interesting radius 2gm, right? And everything we said so far is that all the trajectories which we derived was for r greater than 2gm. What we did so far. Right. Now I want to stress that this is the only relevant region when we speak about, you know, most of the universe, when we speak about the solar neighborhood, right? Because as we said, the solar radius is greater than the Schwarzschild radius of an object the mass of the sun. So if you try to get closer to the center of the sun, right, then the Schwarzschild solution will no longer be valid, because once you enter the sun inside the sun, is not the same. Metric anymore. So, you know, what we said is the very relevant and the most relevant for most practical applications, certainly within the solar system. But now we can imagine and envision what happens to an object that tries to get into smaller radii, to a radius which is smaller than the Schwarzschild radius, namely inside the black hole, and we'll see what happens. So for that, let's consider, so let's say, okay, now relax this option. So consider the light ray that, that propagates radially. Consider a light ray propagating radially. So when I say propagating radially, what does it mean? If I look at the Schwarzschild metric. What does it mean propagating radially? What would be the mathematical description of that? Yeah. Come on, I'm asking you that in an exam. You cannot just sit down now and then stare at the question. When it says propagating radially, what does it mean?
The omega equals 0.
Thank you. Right? The R is changing, the T is changing, but the omega is 0 because it's radially, right? So that means that the omega is equal to 0. When I say a light ray, what does it mean when you look at mathematically at the Schwarzschild metric?
ds squared equal to 0.
It's a what?
ds squared equal to 0.
Thank you. Very good. Right? It's a null geodesic, right? Excellent. So ds squared is equal to 0. So I'm going to write down the Schwarzschild metric now. ds squared is equal to 0, right? It's just a minus 1 minus 2 gm over r dt squared plus 1 minus 2 gm over r. minus 1 dr squared. Okay. So we can, you know, just put directly, right? Just move this to the other side. It's 0 anyway. And we can write down dt over dr, right? It's just a plus minus 1 minus 2 gm over r minus 1. Right? Just move this term. Move this term to the right. I divide by 1 minus 2 gm, and here I divide by dr, and I get this t over dr is this plus minus 1 over 2 gm to the power minus 1. Right? Now I want to draw that. So let's draw that in this TR diagram. So we R, so we T. And let me mark this as 2 gm. Now I want you to have a look. The T over the R is plus minus 1 minus 2 gm over R to the power minus 1, right? So if I'm in a very large R, what is the T over the R?
1.
1, right? So plus minus 1. So that means that the slope of this light cone, remember we're talking about the light, is going to be exactly 1. Right? Now what happens when we get closer to, you know, the Schwarzschild radius, 2 gm? The slopes gets, right? What happens to when we are exactly at R equal to gm?
Diverges.
Right? What is the TDR?
It's diverged.
It goes to plus minus infinity, right? We have a 1 minus 1, which is 0 to the power minus 1, so that gives you infinity. So as we're getting closer and closer, right, the slope, the T over the R is really the slope here, right? So the slope is getting smaller. Right, you're seeing what happened. I mean, this is the light cone, right? So this is, I'm here now, right? I'm here. We're talking about lights, right? So I can go in this direction, right? Within the light cone. When I'm far away from the black hole, right, I can go either closer or further away. There's no problem. When I'm getting closer and closer, right, it seems like I can never reach this event horizon. Right? I can never really reach it. Right? Rather that I'm asymptotic. Now you realize that there's something really interesting happening here. Right? As I'm approaching, as the light approaches the black hole, right? It takes longer and longer time. So if I go like that, it takes longer time. It will seem to never approach it. Never cross it. Now, of course, this is really illusion in some sense, right? The light ray will cross the event horizon, right? There's no problem for the light ray to reach the event horizon. But what does it mean, what we have in here? I mean, these coordinates, the T and the R, right, are for an observer at infinity. So that means that for an observer at infinity, he will never see the light or anything massive, right, crossing the event horizon. Right? Let me write it down. Right? the light ray or any massive object. Never seem to be able to reach the R equal to GM.
Stuff.
Yeah.
So for an infinite distance observed, if he looks at an astronaut approaching the horizon, so when the astronaut passes the horizon, so will he see him freeze on the horizon?
You will never see the astronaut crossing the horizon. What will you see? Remember we discussed that last time when we discussed the gravitational redshift, right? Let me discuss that in a second, right? Oh, well, I can discuss it now, right? So you have an astronaut that tries to reach closer to the horizon, right? And this astronaut is sending signal to his friend, which is on the spaceship. Now, what will you see? Let's say that the astronaut sends signal, you know, every second, right? I'm okay, everything is fine, nothing special, nothing special, nothing. What will be observed? What will happen to the signals?
We get redshifted.
Exactly. First, they will get redshifted, and then the second thing, what will happen?
At the horizon, the signals would stop.
For the horizon. You know, this astronaut is traveling towards the horizon, and he sends signal. Oh, my time now is 2 o'clock. Now it's 2:01, 2:02, 2:03. What will he see? What will be observed by the his friend at the spaceship?
Well, signals will get further apart. They will get further apart from each other.
Exactly. They will get slower and slower, right? That's exactly what we have, right? We're getting deeper in the gravitational potential. It will get slower and slower and redder and redder. Say, I'm okay, I'm okay, I'm okay, I'm okay. Right? Now the astronaut here will never be able to see this astronaut crossing the horizon because it's going to take an infinite amount of time for the signal to reach the observer. Now, of course, from the point of view of this astronaut, there is no problem. He might not even notice that he crossed the horizon. Because as we said, there's no singularity in the horizon. The metric is curved there, like in any other place. Okay, but from the point of view of the guy here, you know, you see the astronaut getting redder and redder, and the signal from the astronaut getting slower and slower and slower to infinity. He will never be able to see the exact time in which this astronaut crossed the horizon, because it's going to take an infinite amount of time once it reaches the horizon. Huh?
No, Asaf, I'm not sure I'm understanding, because if we said this radius is just an artifact of the coordinates, so why does he have some meaning? Maybe I can switch, distance observer can switch coordinates and everything will be fine from his point of view also. I don't know.
Hey, wait, we'll see that. If you don't feel you understand, you're in a good shape. If you tell me that you feel you understand, I would be much more worried. But yeah, we'll get to that in a few minutes time. Okay, but you know, the t and the r, these are the coordinates, right? The time and the r coordinates. And at infinity, infinitely far away from this source of gravity, there are just Minkowski spacers. These are the time and radius coordinates that we're used to. Right? From the point of view of somebody at infinity, right? This astronaut, not particularly wise guy, is just going to be seen getting redder and redder and slower and slower. The signal from him will get redder and redder and slower as he approaches the horizon. This right. That's I'm going to answer your question, but one step at a time. You will get answer before the end of today's lecture. So, but the light ray never seemed to be able to reach our 2GeM, but this is an illusion. The light ray as well. Yes, and massive object. Actually reach this radius without any problem. Right? Okay, so I told you there is something. Let's start to basically answer your question and decipher what happens one by one. So there is something which is very tricky happening there. On the one hand, and this is fully consistent with what we spoke about gravitational redshift in the last lecture, right? An astronaut and infinity will have will never see the observer or the astronaut or a signal coming from the event horizon, reaching it in a finite amount of time. But then on the other hand, I said for the astronaut, there is no problem crossing this horizon. It can just keep on going and it will cross the horizon at a certain point without even noticing. Meaning, in fact, it will cross the horizon in a finite amount of his or her proper time. Okay. So while an observer at infinity will never see an infalling particle crossing the horizon, crossing this radius. The infalling astronaut will cross it in a finite amount of its proper time. Okay, so how can this be? Well, for that we need to start playing with the coordinates and start manipulating the coordinates a little bit and see what happens. So let us understand what happens. Okay, so the real problem is that we have here an infinity, right? The T over the R is plus minus 1 minus 2GeM of R to minus 1, which goes to infinity when R goes to 2GeM. That's the problem. So in one sense, you can say that the as you're getting closer to 2GeM, the progress you can make in the radial direction is getting slower and slower. Right. So one way out is we may simply manipulate the coordinates. Let's manipulate the time coordinates such that the moving down to smaller r will not take infinite amount of time. Right, so let us manipulate or change the coordinate so that it will take finite amount of time to reach 2GM levels. Okay. So the first thing we're going to do, we have this equation here, which is this one. We can simply integrate it, right, and we solve it. So we can take this equation and solve it by integrating, and we end up that t is equal plus minus, maybe I should just write it back. Write it again. So let's take this equation. Okay, so I'm taking this equation, and now I can solve it simply by integrating, right? I have the t over the r. So I can have a direct integration, and I have that, by solving that, we have that t is just plus minus r star plus some constant of integration, right? And r star is just r plus 2gm ln of r over 2gm minus 1. Right, that's an integral which you can do. Right. Now this has a name. You can just plug it. If you don't believe me, just plug this result in here, and you see immediately that solves it. This has a name, the r star. It's called a Tourtois coordinate. Tourtois, right? R star is called Tourtois coordinate. Now we can replace r with r star with the Tourtois coordinate, and we write down the metric. So using t and r star, the Schwarzschild metric, ds squared is 1 minus 2 gm over r, and then minus dt squared plus dr star squared plus r squared d omega squared. Right. Now basically when I write it like that, I can think of r as a function of r star. R is r of r star. Okay, that's not too bad. That's not too bad. This Schwarzschild metric written in these terms of this t and the Tourtois coordinate. Because what we have, right, is that both GTT and G R star, they are, they become 0 at r equal to gm, but none of the metric coefficients become infinite. So we don't have much of a problem now. Now, when R is equal to 2gm, right, that essentially means that R star goes to infinity, right? So R is equal to 2gm, then R star becomes now infinity. Oh, sorry, minus infinity. R equal to gm, then it means that R star is now minus infinity. So in some sense, we took the radius of this event horizon to be at minus infinity, right? Now we don't really need to define this total coordinates at R, which is smaller than 2gm, because physically it's not clear what they mean there. If R is equal to minus infinity at 2gm, but it's handy from a mathematical perspective to define them. So now, when we have this Schwarzschild metric, we can again make this plot of R star and T. So again, now you see that in these tortural coordinates, the slope, right, dt over dr star is always plus minus 1, regardless of where we are. So the slope always looks like that. Where the light comes. Well, that's true for every radius. Like here we had that the TDR gets to infinity, but here we never have it, right? It's independent on radius, as you can see from, just looking at the T to the R star, because they have the same coefficient. So of course, the price that we pay is that now R equal to gm is pushed to infinity. All right. So I'm doing some mathematical manipulation, not clear what it's good for. Right? That's how the light cone would look like. Okay. Now, if we want to proceed, the best way to proceed is now to define new set of coordinates which are best adapted for null geodesics. So we now define, so next we define, by the way, questions about what we're doing here? It can be a bit confusing, these, we haven't really plotted these light cones before. So now we do them, so I want to make sure that you're with me.
Stuff?
Yeah.
Can you say again why does this change help us?
Yeah, because we don't get infinity. That's the only thing that it helps us really. We are going to change the coordinates in several steps. I mean, I cannot, I'm trying to motivate why we're using this set of coordinates, but of course you could choose whatever coordinates you want. It goes back to the question that I was asked by David. I mean, okay, how do we know that something special happens there, and can we simply change the coordinates? And so that's what I'm doing now. I'm changing the coordinates. I'm just trying to give you some physical motivation of why people have chosen to change the coordinates in such a way and not just select any other coordinates in a random way, right? So it's not going to be a random way, obviously, because you want to avoid infinities. You want to have a metric which is well behaved, namely that you don't get any singularities. You can take the metric, take the inverse of the metric, etc. Right? So that's a physical motivation. But mathematically, it's a mathematical manipulation. You could do it could select your old coordinates in principle. Nothing prevents you from doing that. Right? So, right now, we define new coordinates which are particularly adapted for geodesics. So this would be u tilde, which is defined as t plus r star, the total coordinate, and v tilde, which is t minus r star. Okay, why is this useful? Again, when you look at the metric written in terms of t and r star, then you notice that when we talk about an infolding, radial null geodesic, radial means the omega is equal to 0, right? Null, ds squared is equal to 0, geodesic. Then what can we say about u tilde? What can we say about u tilde? Then it's a constant, right?
Asaf?
Yeah.
But before you had we had a plus minus r star. Doesn't it matter?
Why do we r plus minus r star? I changed the r coordinate with the Tortua coordinate, r star.
And the equation is t equals plus minus r star.
So the TPR, you mean?
Hmm?
No, this is the metric, right? This is the metric.
Yeah.
Right now, when you are now you're separating, right? There is an infolding, right? This guy here is infolding. Namely, its radius gets smaller, so it falls inside this black hole, which we haven't stated as a black hole, but you get the idea. And this guy, r star, increases with time. So it's outgoing.
I'm saying because of the square, it's plus minus. So it's
Well, I have here a minus dt square plus dr square, dr star square.
Mhm.
Right? Now, in a null geodesic, this is 0, the s star is 0, the omega
yes,
is 0, right?
I understand, but
Now,
we get
okay. Now, when I say infolding, why did I choose u? Why do I tell you that u is constant? Right? So what you're asking. So for an infolding particle, as time increases, r decreases, and so r star also decreases, right? Because r star is depending on r. So for infolding object, t as t increases, r, and therefore r star decrease. Right? Now, du tilde, right, is just dt plus dr star. And from here, right, we have that dt's have to be the minus, right, because r star decreases as t increases. So we have to take the minus sign for an infolding object. For infolding object, then decreases, then we have dt is minus dr star. And so together that means that du tilde is just 0, and so u tilde is constant, as I just wrote before. right? Now, of course, what is v tilde? When it will become constant?
No outgoing.
Or an outgoing. It's symmetric. So the next step we're going to do is to replace the coordinate t with the new coordinate u tilde. But we want to keep the r coordinate. So the next step, so this is the second step. And the third step is to replace t with u tilde and keep r. Now these have a name, so let me write down the result. The result is that we have the ds squared is just minus 1 minus 2 gm over r times du tilde squared plus du tilde dr plus dr du tilde plus r squared d omega squared. Again, this is the same Schwarzschild metric, but now I wrote it rather than time, I replaced the time coordinate with u tilde coordinate, which is defined in a little bit complicated way. Right, it's t plus r star, and r star is a function of r. Now this has a name. These coordinates, these are called Eddington-Finkelstein coordinates. So I should write down, these are Eddington u tilde and r, these are Eddington-Finkelstein coordinates. And this is how the metric looks like in the Eddington-Finkelstein coordinates. Now you can look at this metric. There are some nice things here, right? So if you look at G U, right, it is equal to 0 when R is equal to 2 GM, right? This is GUU, right? So when R is equal to 2 GM, it's equal to 0. But there's no degeneracy, right? We can take the metric, we can take the inverse of the metric, we can take the determinant of the metric, add this radius, there's no problem. Right? So if you take, what is the determinant of the metric? Right, now it's G, right, the determinant. We have U R theta phi. 1 minus 2 GM over R. And then 1, 1, 0, and then R squared sine squared. Right? So G just minus R to the 4 sine squared. No problem. It's regular. That's R equal to G. No need to worry. If it's regular, that means it's invertible. I can invert this metric. Right? Now, because it's regular, that means that I can extend this metric also to smaller radii. I don't have to limit myself to radii which is greater than 2 GM. That's still fine. Right, so I can invertible, so I can can extend to all r greater than 0. I don't get stuck with some irregularity or things that are not inverted when I go down to r equal to gm. Yeah? Shaky? Fine. Okay. Okay. So if we look at these Eddington-Finkelstein coordinates, right, and the condition for radial null curve, Eddington-Finkelstein coordinates, right? Again, radial is, you can remove the omega, it's just 0. Null is that ds is equal to 0. So I end up with du over dr is, well, now I have to be careful. If it's infalling, right, then it just is 0. And if it's outgoing, then it's just 2 times 1 minus 2 gm over r. Minus 1. Right, I just need to take du over dr. U tilde, sorry. U tilde over dr. Right. Let's draw that so we can fill in. So that's r. That's r equal to 0. That's r equal to gm. So for the infalling, we always get a 0, which means that we can always go in the radial direction. This is u, right? U is not changing. For the outgoing, when r goes to infinity, we get du over dr is 2, so it will be something like that. Right? Now, what happens when r is equal exactly to gm? What is the slope for the infalling? What is the slope for the infalling?
No slope, constant.
Still 0. So you can still get it. No problem. What is the slope for the outgoing?
Infinity?
Infinity.
Asaf,
Yeah.
can you maybe explain what these diagram are? Why do you...
These are the light cones. These are the light cones of a particle. Let's say that there is a particle.
Ah, okay.
Which is here. Maybe I should plot it with a different color. I don't know. A particle that is here. And I'm asking myself, okay, I'm looking now at these coordinates, the same that I did with the r and t coordinates in the Schwarzschild, and then that I did with the r star and the t coordinates in the George-Wa coordinate, right? And I'm asking myself, okay, now I'm here. This is in the RNT, so it's easier to visualize. Where can an object here be, propagate into the future, right? So it can either go in this direction or in this direction. It can be anywhere within this light cone. It cannot be outside of this light cone, right? And we just show because that's given by this dt over the r, right? So it's somewhere within this light cone, and this light cone gets narrower and narrower as we get approaching closer to the special radius of 2gm. Now I did some manipulations, and I replaced this t and r with u tilde and r, the Eddington-Finkelstein coordinate. And now I'm asking exactly the same question: how the light cone looks like from the point of view of a particle. So when the particle is at r in these coordinates, so now the coordinates are r and u tilde, right? I replaced the time with this new u tilde. And what I got is that du tilde over the r for infalling particle, right, is just 0, right? Because u tilde is just constant. And for an outgoing particle, it is just 2 times 1 minus 2gm to the power minus 1. So let's draw that. And when we draw that for r, which is very large, right, 0 meaning that it can get to smaller u tilde region without any problem, right? U tilde is not changed, it's constant. And for outgoing, we can still have that, it goes with a slope, which is now 2. It's not 1, it's a 2. So it's a bigger slope, but it's just a matter of coordinates. Now, when r is equal to 2gm, for the ingoing slope, nothing changes, right? It's just, you can still keep on going inward in this coordinate. For the outgoing, now the slope becomes infinity. Now, if we proceed and we are at smaller radius, right, then again, getting inward, we still proceed. But now, since r is smaller than 2gm, all the light cones will be looking in this direction, basically. Now, this is quite important, right? Because that tells you what are the future directions that you can go, right? When you are here, in your future direction, you can get in the direction of smaller r, or in the direction of larger r, right? R decreases to the left and increases to the right. But once we cross this r equal to gm, right, then we look at all the trajectories of the outgoing photons, then we find that du tilde over the r is always greater than 0 for r which is smaller than 2gm. So once you cross that, right, all future directions point inward, points toward decreasing r. So there is something very important happening in this radius of r equal to gm. What is that? We said in these coordinates, we can clearly see that is now answering the question that I was asked earlier, right? Nothing special happens to the metric there, right? In this coordinate system, the Eddington-Finkelstein coordinate system, the metric is regular, it's invertible. There's nothing special happens to the metric at that radius, right? What I told you, you can cross it, you won't even notice. It's not a singular point, nothing special happens, right? But something does happen. And what is that?
You can't escape the region.
Exactly. Once you crossed it, once you're inside this region, all your future direction, right, will point inward. Right? So locally, this surface is perfectly regular. But globally, this is a point of no return. Once you crossed it, all your future direction will take you inward. A particle that crosses it can never come back. So nothing that happens in this region, you don't know what happens here. Whatever happens in this region cannot communicate to the outside world. Because any event that takes place here, right? A particle is created, destroyed, something. I don't know what happens there because everything, all the future directions will take you towards the singularity at r equal to 0. So many things may happen there. But as long as I'm here, I have no way of telling. Right? So locally, this is perfectly regular. But globally, r equal to gm is the point of no return. Right. So what's the other name of this radius?
Schwarzschild radius.
We said it's Schwarzschild radius, but what's the other name because of this point of no return?
Event horizon.
This is the event horizon. This is the name event horizon. Any event that takes place inside can never communicate to the outside world. So no event that happens at r smaller than 2 gm can influence any other event that happens at r greater than 2g. So since nothing can escape, right, that means that we cannot see anything from the inside. Right? Many things can happen here. You can see, right? But whatever happens here can never communicate to the outside. So if we try from the outside to look inside here, what will we see? What will we see? Yeah. If I'm from the inside, I'm trying to look out and probe what happens inside. What am I going to see?
Normal.
What?
You would look. You see only something that at a larger radius.
Yeah. So what will I see from here? Nothing. Right? No signal can cross this backward, right? This is what this is showing. Right? No signal, nothing that happens here can ever cross the horizon backward. So I will see nothing. So how will I call that? How will I call that? You know the answer? Come on, guys.
Black hole.
Thank you. What did we do? We started from the regular coordinates, right? The TNR coordinates. But we saw that we cannot get a very good description of the entire manifold because if we look along geodesic, once we reach the R equal to GM, then they become infinite, right? So we made some changes, right? So we changed. So it started from TR. And then we changed to U, or under some motivation, which I tried to explain to you where it came from. And, you know, in these coordinates, right, as R decreases, U is constant. And R decreases along no curve. Right, and U is constant, which means that there is no problem for us to get right through the event horizon. Nothing prevents us from getting through the event horizon. Right, we can simply go in, no problem. So, you know, this is something which is kind of difficult to imagine, but you know, if you have an astronaut that goes through the event horizon, the astronaut will not necessarily even know that. You just go straight in, no problem. Nothing prevents you from doing that. You won't feel anything special when you do that, contrary to many science fiction beliefs. So the metric is just sorry? Because locally, when you look at the metric locally, it's not different than anywhere else in this vicinity. I cannot hear you. If there's somebody trying to ask a question, I cannot hear. There is a shortage of communication. Does anybody want to say something?
Yes.
Please say it again because I could not hear.
That falling into the black hole should be spaghettified, isn't it?
No, you're talking about a different thing. The spaghetti that you're talking about is something else. You're talking about what's called tidal forces. But that really depends on the size of the black hole. If the black hole is too small, what will happen is that the difference in the gravitational force that you'll feel in your feet and in your head will be so large that it will tear your body apart. This will happen at a certain point. But it doesn't have to happen at the event horizon. It depends really on the size of the black hole. If you're an astronaut and you don't pay attention, since locally, we said that locally the geometry there in the event horizon is no different than the geometry anywhere else in the vicinity. You can simply go on straight, you won't even notice. But once you get in, there is no way out. And even more, if you think of it, since all future directions takes you towards smaller r, once you enter, you don't have even any way of staying at the same radius. You will get down to the singularity. It's not going to take you very long. And yes, at that point, you will be torn apart because of these tidal forces, namely the difference in the gravitational force of your feet and your head. And of course, if you want to live longer, the best thing to do is nothing, because you live longer along geodesic. If you try to change your path, you live the geodesic, it will just take you shorter. Yeah? Cool? Now it's going to get even cooler. Did you notice something strange in what I did? I did some mathematical manipulations, but I did something here that broke the symmetry. What was that? What was that I did? Did you see something strange in what I did? Something that you should have, if you pay careful attention, it should have alarmed you. Should have caught me and saying, ha ha ha, what are you doing here? There was one thing which I did, which was my choice.
And you used U?
Yes, I used U tilde. Right? What happened if I were to use V tilde rather than U tilde? Right? Rather than U tilde, I could have chosen V tilde.
This will be a white hole, something?
Yeah.
This will be a white hole?
Yeah. What will happen in this case? Then the metric would be ds squared is minus 1 minus 2 gm over r dv tilde squared minus dv tilde dr plus dr dv tilde plus r squared d omega squared. Right, so now I have a minus rather than a plus that I had previously. So what happens now? Now I can also pass through the event horizon, but now in the other direction, right? So if I repeat the same argument that I did previously, right? Now V tilde would be constant for outgoing objects. So now if I have to plot, right, R V tilde, right, R equal to 0, R equal to GM, right? Then for outgoing, I always have a flat, and there will be a minus 2 here. And at the event horizon, I have that, right? And inside, I have all future directions will take me outward. What's going on here? Oh, I'm sure I got you really confused. So what the hell is happening around here?
Everything that is inside the R equals 2 GM is shooting out.
Shooting out, right? So how can it be? So what happens there? Is R equal to GM is a black hole or a white hole? Or what the hell is going on here?
Point of view?
No. It's not a point of view. Now we need to go back to the way I define these coordinates, U and V, right? Which are defined here, right? Because if I keep U constant, right? If I keep U is constant, and I decrease R, so decreasing R means decreasing R star. What does it mean about the time?
Increasing.
Increasing, right? Time goes to infinity, plus infinity, essentially. And if I keep V constant, and I'm decreasing R, what happens with the time?
Decreasing.
Well, the opposite, right? The time goes to minus infinity. So we're really extending the metric to all future passes and past passes, right? So for constant U tilde, right, R decreasing means that T goes to plus infinity. For constant V tilde, R decreasing means that T goes to minus infinity. Okay, so there is time involved here, which is obvious. So in order to see the full picture, we need to do a little bit of more manipulation, and that's called essentially going to lead us to what's called the Kruskal coordinates. So the manipulation goes as follows, right? So we're again going to introduce new set of coordinates. It will be U prime and V prime. So introduce new set of coordinates. U prime, which is E to the power U tilde over 4GM, and V prime, which is E to the power minus V tilde over 4GM. And I can write those in terms of the original time and R coordinates. This will be R over 2GM minus 1 to the power 1/2 E to the power R plus T over 4GM. And here it will be equal to R over 2GM minus 1 to the power 1/2 E to the power R minus T over 4GM. And if I write down the metric in these new coordinates, then it will read ds squared is minus 16 GQM cubed divided by R, E to the minus R over 2GM, and then du prime dv prime plus dv prime du prime plus R squared d omega squared. So now we can clearly see that the metric is not singular at 2gm. So at r equal to gm, there is no singularity at all. Right. All the metric coefficients behave very nicely. Nothing special happens to the metric coefficient, right? Now we could stay with that, but we don't want to because u prime and v prime are null coordinates, namely the partial derivatives are null vectors. And we prefer to work with something which more resembles t and r. So so u prime, or I should say d over du prime and d over du prime are null vectors. We want a coordinate system one time-like vector, time-like coordinates. It's really space-like coordinates. So to do that, again, we define u as 1/2 u prime minus v prime, which is r over 2gm minus 1 to the power 1/2 e to the power r over 4gm, and then cosine hyperbolicus of t over 4gm, and v, which is 1/2 u prime plus v prime, which is r over 2gm minus 1 to the power 1/2 e to the power r over 4gm, and then of course sine hyperbolicus of t over 4gm. And in terms of these yet new coordinates, we write the metric ds squared as 32 g cube m q over r. So we write e to the minus r over 2gm, and then minus dv squared plus du squared plus r squared d omega squared. Where for r, to get r, we simply make this algebraic properties. We just have that u squared minus v squared is just r over 2gm minus 1 to the power times e to the power r over 2g. Get r. Okay, so these coordinates u, v, theta, and phi, these are known as the Kruskal coordinates. Sorry, it should be v and u because v is the time-like vector. So v, u, theta, and phi. Now, in order to avoid this kind of confusion, I just said, then the textbook by Carroll actually uses that as a t, and this is an r. But this is just a rotation, the same coordinates. In older textbooks, it's v and u. What is dvdu?
One or minus one?
Plus minus one. So dvdu, just plus minus one. Okay. Now, these Kruskal coordinates, these ones, they are actually have some miracles, some miraculous coordinate system. So let's see. We're talking about the radial null curve. How does a radial null curve look like? Again, radial means that the omega is equal to 0. Null means the S is equal to 0. So how does a radial null curve look like?
Like a cone, like.
Well, we just have a, well, it's very easy, right? This is 0, this is 0, this is just constant, so we don't care about it. So you just have minus dv squared is equal to du squared, right? So it just means that dv is equal plus minus du plus some constant. Now, where is the event horizon? Event horizon. Right, that's r equal to 2gm. So where is the event horizon? In these new coordinates?
0, 0?
No, q and v are not 0. Right, you actually see it from here, right? If r is equal to 2gm, then we have u squared minus v squared is equal to 0. So that means that v is equal to plus minus u. Right?
When you define the v and u, you wrote r over 2gm minus 1 square to the power of 1/2.
Yeah.
If we substitute r equals 2gm, isn't it 0?
That's a good point. That is something that well, the problem would be that you get to. Okay, I don't have an answer right away. I have to think a little bit about that. So I'll give you an answer on Sunday for that. From here, okay, that's an interesting point. I'll mark it to myself. So from here, you got that they are equal to gm. Okay, I don't see that right away, so I'll have to think of that and I'll give an answer on Sunday. Okay, in any case, from here, it's clear that u is equal, v is equal plus minus u. And a constant r in general, right? Constant r, right? Then we have that u squared minus v squared is just a constant. And constant t, well, we just need to divide, and we get that V over U is just tangent hyperbolicus of T over 4GM. So this is just a straight line. So this is U, this is V. So R equal 2GM and T goes to infinity. I guess that the answer to your question should be that T is infinity here. That's why it cancels out, because you have an infinity times 0. So and then you should do it in a different color. So this is R equal to GM, T equal to infinity, R equal to GM, T equals to minus infinity. R equal to 0, when R is equal to 0, right, U squared minus V squared is just minus 1. So R equal to 0 looks something like that. This does not exist in space. This is R equal to 0. And here as well, R is equal to 0. And then constant T, simply be straight lines. Sorry for my bad drawings. Constant T means that these are straight lines. Then constant R, so that U squared minus V squared is constant, so constant R would look something like that, like parabola. What? Now in this system, the light cone is always a plus minus 1, right? Which you can see from here. So the light cone always looks like that, regardless of where you are. Right. Now, I'm taking a few minutes off the time. Let's see. You can divide this into 4 regions, right? So there is region 1, right? Region 2, region 3, and region 4. Where are we? Which of the 4 regions are we?
Two?
No?
One, sorry.
1, right? We're in region 1. We're somewhere here. Some radius which is greater than the event horizon radius, right? 2GM. This is the 2GM. Right? This line here marks the radius of R equal to GM. Right? I mean, in these coordinate systems, U is between minus infinity and plus infinity, right? V squared is smaller than U squared plus 1. Forget about that and fine, right? We are somewhere here, right? Moving along, let's say we're here, right? Moving along constant r, goes like that, right? Now we can go to smaller and smaller r. What is region 2?
A black hole?
This is the black hole, right? This transition here marks the black hole. Right? Once we cross it, we're inside, we're doomed to get to r equal to 0. Right? This is r equal to 0. Right? We're doomed. What is region 3?
The white hole?
This is the white hole, right? But can we ever reach it? Can it ever be reached anywhere?
No,
No, why not?
because you need to be in it to reach it.
Because you need to be at time goes to minus infinity, right? Right. Because to get there, it needs to be to time minus infinity. And minus infinity, you know, the universe did not exist and the Schwarzschild metric was not relevant. Remember, this is only relevant for the Schwarzschild metric. Now comes the really interesting part. What is region 4? Okay, I think this is a good time to end this class. And wish you all a nice weekend. Do you have any questions?
Yes.
Yes.
Can you explain again the R0 part?
Oh, yeah. You just put here 0. Then you get u squared minus v squared is equal to minus 1. Or v squared is equal to u squared plus 1. Right? So these are the lines here, right? This is these lines here. R squared is equal to v squared plus 1. Sorry, v squared is equal to u squared plus 1.
Okay.
And the region here, which I colored, right, it doesn't exist in this coordinate system. All right. Okay. So I'll put the next problem set today at a certain point. So if you haven't had, if you're starting to be slowed down on that, please speed up things. And have a nice weekend.
Asaf?
Yeah.
I have a question.
Yeah.
When we define the u and v, u is it's only positive.
No, why?
Cosinus hyperbole isn't always
of time. Of the time.
Hmm?
Of the time.
Yes.
But there is also an R there. Right? Time can be, first of all, no, I think you're wrong, right? Cosinus hyperbolicus. No, you're right. Sorry, are you right?
It looks like x squared plus 1.
Well, I have to think of that a little bit. I look at that again. Look at that over the weekend. You can discuss something. All right.
Thank you very much. Bye-bye.
See you on Sunday then.
Bye.
Bye. Have a good weekend.
Yeah, please. Any more questions?